now, for the honor of the camera. I'll change language and thereby speak slower, which is probably good, because it might be more complex for you, as it's something that you maybe don't think about too often, even though you mentioned that you think a lot about dust in your daily life in your office. Then hopefully I can tell you that dust is a very interesting thing, and it has many interesting properties. So my research topic is cosmic dust, and I'm at the Dark Cosmology Center at the Niels Bohr Institute, and the reason we call it the Dark Cosmology Center is because we're interested in everything that does not shine, everything that blocks light. And that is very ambitious when you are an astronomer, because I don't know if you ever wondered what astronomers are, but basically astronomers are bookkeepers of light particles. We sit with our telescopes and then we count light particles at different wavelengths. And we put all the red ones in one box and the green ones and the blue ones. And then from that we try to make fantastic stories about how the universe is formed, how it's evolved, and what a star is and what a planet is. But basically we only count light particles. So if you want to write a research application which is different from everybody else, you say we want to look at everything that's dark and doesn't shine. And that makes perfect sense if you stand out at dark night, because you have the shining stars and then you have most of all the black stuff that doesn't shine. So it makes sense, but it's a bit ambitious. So when I see a picture like this, which is the Eagle Nebula in our own Milky Way, then what interests me is the dark clouds, because what you see here is gas and dust that blocks the light from the stars which are behind. So you have as many stars here as you do here, you just don't see them because they're behind the dust. And that you can get dust to be a research topic probably shows you something about that any topic is interesting once you get into the details. Because I think when I finished my master's, anyone has said you're going to end up being an expert in dust, I would have said that sounds really, really boring. And I do get lots of interesting jokes at work, right? Because it's the woman who sits on the dust, and you are the dust expert, and you are the woman. And I'm really good at different cleaning jokes, but if you have some new ones, I would like to hear them. But as we are a very mixed crowd, and some of you might not have much knowledge of astronomy, then I thought I'm going to convince you that astronomy is very, very simple. Because basically, if you look into the universe, there's only two different kinds of objects in the universe. There are stars and there are planets. Then there's something we call galaxies, but galaxies is nothing but big collections of stars. So a galaxy is just 200 billion stars lying together in the universe. So a galaxy is just a stellar cluster, basically, or an island of stars. So you have stars that shine, then you have planets which do not shine, they do not produce energy, and that's basically the difference between a star and a planet, is that stars produce energy. The reason we can see the planets is because there's a star, in this case the sun, shining on the planets, and then you see the light reflected from the planets. So there's only two objects, so it's quite easy. You can do it on one hand, even if you're short of a few fingers. So astronomy is easy. You have the stars and you have the planets. Then, of course, when you look into the details, we have different kind of planets. We have like Earth-like planets, which has a surface which you can fly to with a spaceship, and you can walk around on the surface. Then we have the gas planets, which are basically just big lumps of gas. So in theory, you can fly through them. In reality, you can't, because gas gets very dense and your spaceship is going to get squashed. But in theory, there's no way you can land. You can just move all the way through the planet. And as stars are also big balls of gas which produce energy, then really the only difference between the gas planets and the stars are the size. So if you're a big gas planet, then you get big enough that in your center you get a high enough temperature that you can start producing energy. So one could wonder whether planets are just, failed stars somehow. They're just stars that weren't not big enough to become stars. So maybe there's only one type of object in the universe that's stars. And then there's some stars that just never got around to shining, which we call planets. So if you stand out at dark night, and it has to be really dark, so you have to be outside of Copenhagen, then you might notice that there is this sort of diffuse band, which looks like little clouds of stars across the sky, which is what we call the Milky Way. And all cultures have stories about why you have this shining band of light. And even since the old Greeks, we've been wondering, what does that mean? And the way we interpret it is we think, okay, if you probably have something like a flat plate of stars, and then the sun is also a star, so it's probably sitting somewhere in this flat circle of stars, and then we'll be trying to find out, do we sit in the middle, or are we sitting out in one of the edges of all the stars? And one way to do that is, of course, you just count all the stars in different directions, and then you think, okay, if you have the same number of stars wherever you count, then you're probably sitting in the middle. If you have more stars in one side than the other side, then we're probably sitting a bit out at the outskirts. And And astronomers have done that since the ancient Greeks, and they reached the conclusion we're sitting in the middle, because you see the same number of stars wherever you count. And the reason they reached that conclusion is because they thought that what you see here as black patches are really clouds of gas and dust which blocks the light from stars behind. But it wasn't until 1930 that astronomers realized that you do have dust in the universe. So the fact that they didn't know about dust made them come up with the wrong conclusion that we're sitting in the center of the Milky Way. Trying to find out what the galaxy, the collection of stars that the sun is a part of, which we call the Milky Way, what that looks like is very difficult because we're sitting just among all the other stars and we cannot fly out and see us from above. But we do believe that if we could, then we would see something like this. So this is a model. It's not a picture. It looks like a picture, but it's not. It's a drawing. And we think we have the sun out here, not in the center, but out here in the outskirts. We have realized that's a very good place to be because the stellar concentration, the amount of stars in the center, is very dense. So you have lots of nasty radiations. I mean, the sun is nice on a day like this, right, when it shines, but the sun also sends out lots of other types of radiations which are not good, like ultraviolet light, which gives us cancer, and X-rays and all kind of stuff. So it's good to be on a planet like the Earth, where we have the atmosphere and the magnetic field that can shield us from all the nasty stuff from the sun, and to be far away from all the other stars, so we don't get too much of their radiation. So therefore it's quite good to be out here in the outskirts. Today we think that our galaxy is what we call a spiral galaxy, so you have a density of stars here, and then you have the stars lying in spiral arms. And we think that the center is a bit elongated, but it's very hard for us to find out because we're sitting here in the plane of the Milky Way. So when we look this way, and to look this way you have to go to Australia or South America, you have to go to the southern half of the globe. And then when you look at the night sky, you look into the center of the Milky Way. So if you ever get the chance to go south of equator, look up at the night sky, it does look different than it does in Denmark, and the Milky Way looks spectacular, because you look into the center of the Milky Way. So if you want to study our own galaxies, you want your telescope to be on the southern hemisphere. If you want to look out of the galaxy, so from Denmark, for instance, then you look this way, out of the galaxy. So if you want to look at other galaxies, then it's much better to have a telescope, not in Denmark, because we have too many rainy nights. Out of 350 days, we have about 50 good nights and 300 rainy nights. So therefore, we've moved the Danish telescopes to La Palma, the Canary Islands, and there we have 300 clear nights, so it's a much better investment to have our telescopes there, even though we have to pay for the plane tickets. It's still a better use of the telescopes. So from the northern hemisphere we can look out, and from the southern we can look in. And then you can imagine when you look into the Milky Way, then all the stars here are going to block what is behind the center. So we don't really know very much about what's on the back side of the Milky Way, so to speak. We're a bit saved by the fact that the sun moves around the center of the Milky Way once every 216 million years. So in 108 million years we'll be up here on the other side. So if we kept good notes, we can compare and we can see what the difference is. There will of course be stars from up here that has moved down here, so there will always be something shielded. But generally, at least we can look out to the universe and see what's up there, which we currently cannot see because the center blocks what we see. So that's the reason that we've come up with the idea that our own Milky Way is a spiral galaxy is because when we look out at other galaxies, so other clusters of stars, then they are spiral galaxies. So this is our nearest neighbor, the Andromeda galaxy, and we see it from the side. And there you can see there is also spiral arms, and everything that's black here is actually dust lanes. So you have the dust lying along the spiral arms. Then you have two little dwarf galaxies that move around the Andromeda galaxy like the moon around Earth. So you have a system. And it is such that the Milky Way and the Andromeda galaxies are approaching each other. So eventually in some billion years they will be moving through each other. And that sounds quite scary, but it isn't really, because the distance between the individual stars are so big that the galaxies will just move. They'll move through each other, and none of the stars will actually collide at all because the distances between the stars are so. I mean, galaxies, they look like they're very dense, but actually they're mostly just nothing, because there's a very big distance between the different stars. None of the galaxies will look the same after that, because the gravitational interaction will make them look all different once they have moved through each other. But the stars as such will not collide. But it will be a fantastic view in a few billion years, right? When we have the Andromeda galaxy taking off half the night sky. That will be quite spectacular. So if we look at some of the dust and gas that we have inside our own galaxy between the stars, then it looks like this. And it looks rather spectacular, and if you've seen science fiction movies, then I'm sure you are aware that, I don't know if you ever noticed that when you see the spaceship flying around, the way you can tell the difference between the good guys and the bad guys are that the good guys have the very nice spaceships that looks nice, that are symmetric, they're beautiful. And then the bad guys have the ugly spaceships, the one with things sticking out, which are in different directions. And then if the bad guys are after the good guys can fly into a cloud of gas and dust and hide, and then the good guys will miss them. And they're safe. And every time I see that, I just roll on the floor laughing, because it looks very dense, but it's not dense at all. Actually, the distance between the individual atoms is like several meters. And you cannot hide a spaceship between a hydrogen atom here and then one over here and then another one over there. And the reason it looks so dense is just because the distances, the line of sight, as we call it, is so intense. So even though you have very few atoms, then if you have one here, one here, one here, one here, then if you have a long enough distance, it's going to look very compact. And it's the same thing that you experience on Earth when you have a foggy day. Then where you're standing, you can see quite clearly, but over there it looks really, really foggy. But then when you walk over there, then it looks like very foggy where you came from, but it's clear. So it's the same thing here, that if you were sitting inside this, you wouldn't know that you were sitting inside a dense dust and gas cloud, because the distance between the individual dust particles is ridiculously big. It only looks intense because you see it from such a huge distance. So why on Earth worry about dust at all? Because there's almost no dust in the universe. The universe is, so to say, a dream of every Hausfrau. I mean, there's like no dust. It's a really clean place. And the way to give you an idea of how much dust is in the universe, then if you take the Milky Way, then it is such that 1/5 of the part of the Milky Way, which consists of stars and planets and things as we know it. You might have heard about dark matter and dark energy, which has some other properties. But if we just stick to the things that we know, then 1/5 of what we know, and which is part of our daily experience, then out of that 1/5, 99% is gas and 1% is dust. So there is almost no dust in the Milky Way, so you can think, okay, with that little dust, why worry about it at all? And the reason that most of my colleagues worry about it is because they think dust is a pain. Because as an astronomer, all you have is your light particles, and then you have the huge distances, so your light particles are traveling very long distances. And even though you have very, very little dust, then if you have a little dust grain here, one here, one here, one here, it can be very untransparent. And the dust will affect your light. And another thing that affects your light is when it travels over huge distances. So when astronomers come out and wave their hands and says the universe is 13 billion years old, the way we calculate that is because we can see how the light has been affected over the long distance. But then our model depends on whether we think there is dust in that line of path or not. Because if we don't think about any dust, we just think, okay, it's just a matter of the traveling that has made the light tired, then we get one result, and if we assume there is some dust, then we get a different result. So that's why my colleagues think that it's worthwhile paying my salary, because they think dust is really boring, they don't want to do it themselves. But they need someone to tell them how much dust is there and what kind of dust is there. Because dust, as we see it up here in the street, can be very many different things. I don't know if you noticed, if you lie on the beach and you're really bored and you start looking at the sand particles, right? Some of them are black and some are white and some are yellowish and some are more red, right? And that's because they're made of different minerals. And of course, when you send light through that, then if you're more transparent, more white, then the light is going to interact less than if you try to get it through a black particle. And the dust in space has the similar properties. So some of it does not interact very much with light, and some of it interacts a lot with light. So they need someone like me to tell, okay, so what type of dust do we have, and how much is there, and what size is there. And then when I talk about dust, I don't know what image you have in your head, but maybe you have like big dust balls that you find, in my house at least, every now and then in the corners. What I actually mean is like smoke particles. So it is what you see up here in the light stream. So or if any of you have ever smoked, or you know someone who has smoked, and you notice that when they blow out the smoke, then you can see these little particles. So we're talking about tiny, tiny particles. And they're primarily made up of carbon and oxygen, and silicon and magnesium, and aluminum and iron. And that's because that's what the universe consists most of. So that is what we have most material of. So that doesn't mean that you cannot have gold particles. It just means you don't have very much gold in the universe because it's hard to form gold. And that is why gold is always a worthwhile investment, as long as we as human beings agree on gold being worth something. Because there isn't very much gold in the universe. It's hard to make gold. They're only made in supernova explosions. While diamonds, sorry, diamonds are made of carbon. There's lots of carbon in the universe, and you can make synthetic diamonds. It's actually relatively easy. You take some charcoal for your grill, your barbecue, and a few sticks of dynamite, and then an oil barrel, and then you join them all together. And then you will actually have turned your little charcoal into diamonds. They will not be transparent and pretty, they will be all black, but they will be diamonds. So we can risk that the whole market is going to get overfloated with synthetic diamonds. So you being lawyers who might have more money than I have and might think about what to invest in, I think gold is a better investment than diamonds. But of course it depends what your purpose is. So if you're a man and you want certain things, then maybe diamonds will be a better investment. So when you look with normal telescopes where you can see the visible light, then what dust does is it blocks what you see. But it is such in physics that nothing goes away. So when you have a dust particles and it's hit by the visible light, then it gets heated up, and that means that your dust gets a little bit warm. So that means if you look in another wavelength area, which is where you have the warm light sent out, what we call the infrared varmeenergi, then you can actually see the dust glow in itself. So the data I work with is not so much telescopes on Earth. I work on telescopes in space, because you cannot see this from Earth because we have the atmosphere that blocks all the infrared radiation. But if you go into space outside the Earth atmosphere, then you can make some pretty spectacular observations of what the dust actually looks like. So one example is the Spitzer telescope, and notice that you have Earth there, and you have the end of the telescope pointing towards Earth because Earth is warm. So you don't want all the heat from Earth to get into your telescope. And also you have a shield towards the sun because the sun is warm. And then you have to cool down your telescope to as low temperature as you can, because else your telescope is also going to be warm and then you're going to see nothing but your own telescope. So you have to have some really good cooling mechanism. There's the next telescope which we have great expectation for is called James Webb. It's going to be the new Hubble telescope. So when Hubble is finished in 2012, we're going to send up the James Webb telescope. I really hope it will work. It has a very, very big mirror. All the telescopes we have in space at the moment, like the Spitzer, have 2-meter mirrors. And the reason that we have 2-meter mirrors is because that's the diameter of the space rocket. So you cannot make a mirror that's bigger than your space rocket. But on the James Webb, we have made a folding mirror. So the mirror is folded in like this when it's shut up. And then the hope is that in space it will unfold like a flower. And it will be a very big mirror. And we astronomers are very skeptic and very nervous it's not going to happen. But some of the engineers say, we have tried this and it works. And then when you ask them, where have you tried it? They say, it's classified. We cannot tell you, but it works. So the military have probably done this. And they guarantee us that it works. And I hope it will, because if you have a bigger mirror, you can collect more light and you can get better pictures. It's that simple. So it's simply a matter of bookkeeping, right? You just get more. So to show you what things look like if you look at the normal visible light or you look in the infrared where you can see the dust, then this is a galaxy with the fantastic name M51, where you can see the stars and the dust lying here as black patches. And it just had a collision actually, so the smaller satellite here and the bigger satellite are colliding. So you can see the arm of the bigger galaxy is getting stretched out due to gravity. And over here you then see the dust. And so in the infrared you see the dust shining, while the stars are not so visible. So here you actually see the dust lighting up. So this is sort of the dust streams of the galaxy. And this is the visual galaxy where you mainly see the stars. And you can see it's the same galaxy, but they look very different. So that's basically what astronomers do. We want to collect light particles at as many different wavelengths. And then we want to put our pictures on top of each other. And then we get really fantastic views of what the universe looks like. Whether you're Superman looking in X-ray or you're like a normal human being looking in the visible. X-ray telescopes also have to go into space because you cannot get X-rays through the Earth atmosphere, which is very convenient, right? Because we are not very good to deal with X-rays, our bodies, we get cancer and all kind of stuff. But if you start thinking about, so if Superman were on Earth, right, and he looked up to the night sky, he would see absolutely nothing, because none of the X-rays from the universe would go through. And then you wonder, when he looks at Lovis, what is it about her that he really likes? Because if you have X-ray vision, you can just see the bone structure, right? So she must have some really good hips or whatever. But once you start thinking about that, it suddenly makes perfectly good sense why he's wearing his underwear outside his pants, because he can't tell. It's soft materials. Well, where the layer is doesn't matter. And to go back to the gender equality thing, I think that's really something very interesting, which I haven't figured out the answer to yet, is why is it that the role model of men is someone who wears their underwear on the outside of their pants? So one of the reasons that I think dust is interesting and not just something, a nuisance which is in the way, is because dust have some interesting properties which are very important for the reason that we are here in the universe today. Because the dust particles in space, they actually serve as little incubators for molecules. So on the surface of the dust grains, you have atoms landing, and then the atoms bond together and form molecules like sugars and amino acids, and all the molecules which make up living organisms like us. So it's actually on the surface of dust grains that you can form the more complex molecules, which we can observe with our telescopes are present in space. So what interests me is what kind of dust grains do we have out there and where are they formed? And it seems that dust tend to be formed in association with stellar death. So it's actually in the death process of a star. Once the star gets to a point where it can produce no more energy in its center, then if it's a big star, it explodes as a supernova. If it's a small star like the sun, it just sort of diffuses out as what we call a planetary nebula. But in both processes, you form dust grains. And it seems that you need dust grains to form planets. So what my research project at the moment is focused on is when did we form the first dust in the universe, because that's going to tell us something about when could we form the first planet. And I'm quite intrigued about the whole question is, Earth was formed 8 billion years after Big Bang. We have a universe that's 13 billion years old, and you formed Earth 8 billion years into the history. That's actually quite fast. That's actually quite early on, one would say. And the thing I wonder is, could you have done it earlier? Or is it such that Earth actually were formed as fast as you could do the first Earth-like planet? Because it takes lots of dust grains to form a planet like Earth. And maybe the reason that we haven't heard from any other aliens for certain in the universe is because we are the first generation of aliens. We're the ones who are going to send out the message to the following generations that's going to come on the later generations of planets. Because the only thing which is certain about the whole Big Bang theory is that we get more and more heavy elements, we get more and more dust as time goes by. So the likelihood, the probability, the statistical probability of forming life increases with time. So it's more and more likely as time goes by that we're going to find humans or aliens. My way into dust came with, actually, I was interested in meteorites. And meteorites are these rocks from space that comes to us all by themselves. They just fall down from the sky, and then we can examine them. And if you have never been to the Geological Museum, there's a huge rock in the courtyard made of pure iron, which is the center of a no longer existing planet. And that's a fantastic opportunity to study what the center of a planet is, which is so much easier than drilling a 6,000 kilometer deep core into the center of the Earth to find out what's there. So by studying these meteorites, we actually have a pretty good idea of what we think the Earth core is like. But it turned out that some of these meteorites, they had not been part of planets, and they had not been melted, and then they contained pure stardust. And that was quite a novelty for astronomers, because that meant that we could finally get some stardust in our hand. Instead of just, sitting with our telescopes and trying to find out, okay, so this kind of dust blocks the light like this kind of dust blocks the light in a different way, then we have like the footprints of the elephant, and we try to imagine what the elephant looks like, But suddenly we would have some in our hand that we could study with all the details you can do in a laboratory. You can look at it in a microscope, you can see which sizes it have, how it's formed, what it's made of. So that was quite a breakthrough, actually, in understanding stardust. And the most fantastic thing was that the stardust we found most of was actually diamonds. And then you get all excited and think, oh, stars, they sprinkle diamonds, and diamonds is the most common type of dust. And that's very frustrating for astronomers because diamonds don't interact with light actually. So you can actually have lots of diamonds in space without it disturbing our observations. So it's actually very hard to find out whether the diamonds are there or not. But my current theory is that the reason we find most diamonds is because diamonds is the hardest mineral we know. So it has the most highest probability of surviving in space. Because if you're a little dust grain in space and you're out in all this radiation from the stars, then the ultraviolet radiation and the X-ray radiation is also damaging when you're a little dust grain. It's going to sap you. So you only have a certain lifetime in space, but if you're a diamond, you can live a little longer than if you're a little sand grain, which is a bit more fragile. So the types of minerals we found were diamond, silicon carbide, which is what you find on sandpaper if you're a handyman. You have this. Graphite, which is almost diamond, right? It's just a different kind of diamond. And aluminum oxide, which is actually sapphire. So that's another interesting germ. And what we have learned from studying these dust grains and meteorites is we think we can tell a pretty good story about that you form some type of dust in connection with stars like the sun when they die, which is what I call planetary nebula. You form another type of dust in connection with supernova explosions. These two types of dust are then transported into what we call the interstellar medium, which is the gas and dust clouds between the stars. And it's from these clouds that you form new stars, because when you have this cloud and it collapses, then in physics, once something starts to collapse, it will just keep doing so until something stops it. And what actually stops a dust cloud, a gas and dust cloud from continuing collapsing is that you form a star which starts shining, and then the radiation pressure from the star halts the collapse, and then you have formed a star. And then around at least some stars, and it actually looks like that it happens around most stars, you can form a disk of material from where sometimes you can form planets. And currently we know of more than 400 other stars in our Milky Way which have planets around them. So forming planets is not so unique as we thought just 20 years ago, where we only knew about planets around our own star. And then some of the building bricks that did not end up in planets ended up as little meteorites. I could examine them in the laboratory. And the way we did, once we knew we were looking for diamonds, was actually you just take your meteorite and then you pour acid on it long enough and hard enough until you have nothing else left than diamonds, because that's the nice thing about diamonds, they're acid resistant, which means that if you're cleaning, you don't have to take off your diamond ring. Nothing's going to happen to your ring. Your fingers might disappear, but your ring is going to be perfectly fine because the diamond is very resistant. So you just have to get rid of the rest, and that means that the curator at the Geological Museum, he gets a little nervous every time he sees me, because I'm very expensive in meteoritic material, because I dissolve most of it, and I'm mainly interested in the things that can survive being boiled in acid. And then we get these little dust grains out, which we can look at in microscopes. And we do that at the Technical University, and there they are really fantastic. They have some guys that are not shaking their hands at all. So they take these tiny little dust grains, and they put them into epoxy, and then they slice them into thin slices, and then you can see little grains inside the bigger grains, which can tell us about the formation history and tell us something about the density and pressure, the whole stellar structure, and what the star which produced this dust were like. Another source of dust comes from satellites. It is such that there's a few satellites, mainly military satellites, which are so prestigious that it's worth flying up to space, bringing them back down on Earth. And when they do that, they can see lots of holes from dust grains which have bombarded the surface of the satellite. And luckily, sometimes you have little dust grains sitting stuck on the surface of the satellite, which they can then pick up, and then you can study them. And there's actually a homepage where you can go look at all these pictures, and you can suggest research projects. So if any of you are interested, you just write them an email, you suggest them your research project. And if they think it's any good, they'll send you the dust grains in an envelope, and it will arrive by post. And then when you unwrap it, you just make sure you don't breathe, right? Because you don't want to inhale as you open it up, because the dust grains are very tiny, and then suddenly they're gone. And then you can do your study, and if the dust grains survive, you can send them back for someone else to look at, or else it's just gone in the process. A third sort of source of dust grains were from the Stardust satellite, where they sent up a satellite which was built to actually collect different kind of dust. So the satellite looked like this, and it was flying out to meet a comet called Comet Y2. And a comet is just a sort of a big dirty snowball that was left over when the solar system was formed. And when they get close to the sun, then you form this big comet tail, mainly because they evaporate. And when they evaporate from the radiation from the sun, you get the gas, which is mainly ice that evaporates, but you also get dust grains released, so you have this dust tail. And you can see that the satellite here is shielded, simply because the dust grains flying in have a very, very high velocity. And as the spaceship is flying towards it, you get something with very high velocity flying towards each other, so it can be quite damaging. Then it had this little tennis racket, which was filled with material, which it kept up, which caught the dust grains. And then what it actually did, then it had an A and a B side. So on the way up to the comet, it collected interplanetary dust particles on the A side. And then when it came to close to the comet, it turned to the other side, and then it collected cometary dust on the B side. When it was finished, it folded into this little shield, and then it was sent back to Earth, where it actually landed, and the parachute worked. So it actually got a controlled landing, and it was picked up and put into a clean laboratory, because now it gets tricky, right? So you picked up a few grams of dust in space, which have cost you billions of dollars to bring back. And you don't want to contaminate it with Earth dust, which we have in huge quantities. So you have to have a very clean laboratory and be careful. But this is what the sample holder looked like. And then, of course, the big question is, how do you catch a dust grain? Because you have the dust moving in space with something like 40,000 kilometers per hour, so they really move fast, against your spaceship that's also moving. So what they use is something called aerogel, which is a certain kind of very porous glass, which has fantastic properties, like it can carry a huge weight without getting compressed. It's so light that even women can carry it, you know, even with long nails. It weighs nothing. And then it's very, very heat resistant. And that's the most important property, because when you have a dust grain flying in and you're trying to stop it, then it's going to produce a lot of heat on the way. And you want to stop it a bit slowly, so that you don't destroy your dust grain when it hits your aerogel. So that's where aerogel was so fantastic, because it's very porous. It contains lots of vacuum or air, depending on whether you're inside or outside. So you can actually catch your dust grains. But you can see you have a lot of dust grains running off here in the track, and then you only have the center of the dust grain actually surviving. And then you take a little scalpel that they use in medicine, and then you cut out your little dust grains. And that has taken years, so the results are just approaching now, because you've had all these students sitting there, not shaking their hands, digging out the little dust grains which have been studied. So here are such dust grains where you can see the trail, and then you can see the individual dust grains which they study. And you might actually recognize they do look like sand, because this particular dust grains that broke up was the same mineralogy as sand grain. Then this Monday, actually, 4 days ago, we hopefully had a new source of dust, because the Japanese, they had a mission called Hayabusa, which flew up to an asteroid called Itokawa and collected a sample. And it is such, this is the third object in the whole universe where we have landed a mission and lifted it off again. And the two only other objects in the universe where we have managed to put a rocket on the surface and lift it off again is Earth and the Moon. So this is the third object we've been to. All my kids think we've been to Mars because they've seen so many movies, but we have landed lots of stuff on Mars, but we never had anything leave Mars again. So this is the third object where we actually managed to land and lift off. And you can see, I think this is such a neat picture, you can see the shadow of the space probe as it's flying over this little asteroid, which is like 500 times a few hundred meters, so it's just a big potato-like stone. I mean, not nice if it hits us, but you know, it's a small rock in space. So it landed on the surface, it picked up some dust on the surface, we hope. We are actually not sure. And the reason we're not sure is because this asteroid is so far away that it takes the signal, it takes the speed of light 40 minutes to get to the mission and back. So if we send up a signal saying, okay, now you land, it takes 40 minutes before the spaceship hear it. And then it takes another 40 minutes before it tells us back that it has actually done what we have asked it. So you cannot sort of control the mission by a remote control. You have to be fully automatic. And it only landed for half an hour, so that meant we only got the signal after it had left again. And then it realized that the first time it landed that it didn't manage to collect any samples, so they did a second landing 5 days later. And then after that landing, they lost contact for 7 weeks. And then miraculously, they regained contact with the spaceship, but they had lost some data, so they actually don't know whether the second landing had success in collecting dust. So they won't know that until they open the little container in a clean room in Japan next week, and then we'll know if there's anything there or not, or it was just lots of money wasted and 10 years of flying in space, and we didn't get any sample. So I've spoken for a long time in English. If you would like to hear something similar, same speed, maybe even faster, but in Danish, then I can recommend going to this webpage. There's lots of other interesting talks lying there. Like there's my big role model, Jens Martin Knudsen, who also talks about astronomy. There's Lykke Friis, who talks about the European Union. There is Ole Hartling, who talked about ethics. He's the chairman of the ethics committee. So there's actually lots of different interesting talks. So if you're going on summer holiday and driving a car, and you feel it's a bit boring driving a car, then go in there, download some talks, and get upgraded on whatever. If you're more a reading person and you don't know what to give your best friend for a present, I can recommend these fantastic books that I have participated in writing. The one I'm mostly happy about is actually the children's book, and that is actually my mission to do something about getting more women recruited into science, because we want more women into science, but we also want more female students at the Niels Bohr Institute. We have about 25%. We would like some more to come. And there tend to be a bias when girls reach 7th grade, they think physics is boring. My own hypothesis is that's because they're right, because the physics teacher is typically boring, the one you meet in 7th grade. So what we hope is that by writing an astronomy book for the 3 to 7 years old, we might get them so interested in astronomy that they will survive whatever physics teacher they might meet in 7th grade and still keep an interest for physics. We were actually nominated for something called the Orla Prize for Best Children's Book of the Year, but we only became number 2. We lost to Bamse og Kylling. Which I think is not so strange, because the panel were children at the age of 3 to 8 years old. So I was quite impressed we made it as number 2 at all, I must say, and not so surprised to lose to Bamse og Kylling. But I think that's fair, that's perfectly fair.
Fierce competition.
Yeah, that's really fierce competition, right? I mean, because they are quite fantastic when you're 4. So that is what I had planned to tell you. So if you have any questions, then feel free. And I guess we can take questions in whatever language, as long as it's something I understand.
So, what exactly are you going to achieve in your research? I mean, what is it that's going to make you publish in Science or Nature? No, Nature, right? What will you find out that will be so revolutionary and interesting that it will change all our lives and be important? Well, that's what it requires, right? It's really important for science and mankind, etc.
Right now we have these really strange observations of very distant galaxies, so galaxies that were present in the universe very early on. Because according to our whole idea about Big Bang, then is first you had nothing, then suddenly out of nothing everything was created, where you only created hydrogen and helium. Out of that you produced stars. Then you needed a few generations of stars, then you started producing dust, and then you could start forming planets. But what we find is that we find dust in the universe very early on, like 400,000 years after the first stars were formed. So it seems that the first stars, and we find huge amount of dust, almost the same amount of dust that we see today. So it seems the first generation of stars were much more capable or much more efficient in producing dust than the stars are today, and that's weird somehow. So I'm very excited about this, because either Big Bang is wrong, right? So we just, the whole idea that we had very short time is the whole idea about time is wrong. Or else it just shows that the first stars produce dust in a different way, and if you can produce huge amount of dust in a different and more efficient way, you can produce planets a lot earlier on. Meaning that we could just as well have been there a few billion years earlier. And there's nothing spectacular about our time in space, which I think would be a relief, because every time we put humankind at some special place in space, we usually have a wrong theory, right? So I mean, my sort of humble mission in life is to understand sort of the whole dust cycle. When was this first dust, and what was formed, and how did it lead to the being of life today? So when I can explain that, I think, and then of course it's not good for the national product of any country, right? So it's just knowledge, right? But then one of the dust types we have seen in space are the carbon-60, which is a carbon molecule which is formed as a football. And that was first observed in space. Then they found out they could produce it in laboratories. And today it's very important for nanophysics and quantum computing and all kind of stuff. So it turned out to have some fantastic material properties. But they got the idea to produce it in the lab because we saw it in space. So that's usually... And then, I mean, the internet is another good example of something where, I mean, invented by physicists to just move data because we had a huge amount of data. And we never imagined it was going to be a social network or whatever, right? And I think even if we had imagined that we actually had known what we were in for, and we have written a request to the Committee of Ethics saying we want to do this internet, and it's fantastic for moving data. It's going to potentially be fantastic for social networking. However, it's also going to increase crime, and it's going to increase child pornography and all kind of other nasty stuff. Then they would probably say, don't do it, don't do it. You move your data files by car, from Switzerland to Denmark. Don't do the internet. So, I mean, you never know what's going to come out of science. So I think even something as useless as one can say astronomy is, does have an impact on societies in a way that none of us can imagine. And I think science as a whole, you need to move the whole science frontier forwards. That's why we also need to invest in humanities. It's not enough to do natural sciences, because if you look at the ideas we get in natural sciences, it's always connected to the ideas we have of other things in society. I mean, one example from my own universe is, I mean, when I was a child, we sent chimpanzees and dogs into space, right? And we let them die just to find out if humans could survive, right? I don't think you could do that experiment today. I don't think the US wanted to do that experiment today. They wouldn't even think about doing it. So I think even though we think the world is worse and there's more wars, I think maybe, some things are better. I mean, because the fact that we cannot do such an experiment, I think maybe is better. But you can also argue it's worse, because that means you cannot try out medicine on lots of animals, and that means that you have slower development in medicines. And the whole, the polio campaign, right? Where when I was a child, then they completely abolished the copper, hvad hedder det? Pox, yeah, smallpox, smallpox, right? And they did that basically why they went down to the remote places where they hadn't. They said, you're going to get a vaccination or we're going to shoot you, basically, right? And today they cannot get rid of polio, because you have some countries which just refuse to have their inhabitants vaccinated because it thinks it's something bad that comes from the white oppressing power, so they will not let, so, and then there you think, oh, what happened to dictatorship and all the good things about dictatorship which could help us fight diseases? Yeah. So that's why it's so interesting being a human being, I think. What is good and what is evil depends very much on how you watch it. And I imagine that's what makes you guys tick every day in law, right? Is that it depends on how you view it. Yeah.
When do you have a really great day at the office? What makes a great day at the office?
That's to understand something I didn't understand before. So if there's something I've been thinking about, why is it like this? And it can be really trivial. It can be like a formula which I just couldn't get it to add up or something. And there's something where I feel like, wow, I gained some new knowledge. Then I'm really excited. Then I think it's great.
Are you the only one doing dust research in the world?
Not in the world, no. No, we are. The last dust conference I was at, we were like 500 astronomers doing dust. And if you do like small particles, then it is a very wide field, because small particles is also what determines what color paint has, and they use it at diagnostic in medicine, because they think if they can understand how light scatters on small particles, you can do some very fast diagnostics of blood samples. So when we go to the big conference, which are just called light scattering on non-spherical grains, it sounds really boring somehow. Then you have like people working with paint and with medicine and with material properties and astronomers and all kind, just talking about for a whole week about how Maxwell's equations interact with dust grains of different sizes, and that has a huge impact on many industrial things, and so dust is a lot more than we give it credit for.
You mentioned that amino acids form on the surface of dust in space, and
yes.
I guess there's other organic chemistry that
yes.
occurs up there too. How important do you think that might be for the evolution of life? on Earth?
That's a very good question, because just because you find the right bricks out in space doesn't mean you form life in space, right?
Yeah.
So I think maybe what it mainly tells us is that it's quite easy to form these molecules, and that's why we also find them in space, where it's hard to form molecules and it's hard to survive. That just shows that it's easy to form. Because I think life on Earth has probably, I mean, you might get all the building blocks, you know, all the carbon and oxygen and whatever atoms down to Earth, but then everything's been warm and remelted and restructured down here. So the reason you also find them on Earth is because these are the molecules which are most easily formed once you have the abundance of the elements that you have out in space and you have on Earth. So, and I mean, if you take my human body and you count me into atoms, then the composition of the atoms in my body is completely consistent with the amount of elements in the universe. So I'm just made of whatever there's most of. So in that way, I'm not very unique at all. And that's also why I think if we're going to go out and look for alien life forms, we might as well look for someone who does not necessarily look like ourselves. I mean, in shape and whatever, because I think that's quite specialized. But if on the atomic plane, they're going to look like us. You know, if you look at how many carbon atoms and oxygens and hydrogens, it's going to be the same, because they're sort of built from the same pool of material. I have lots of science fiction fans who thinks I have no fantasy.
My question is also related to the amino acids in the dust particles, but when you gave the first impression of dust, you said there was one molecule here, and then a couple of meters away there's another molecule, and it's 3 degrees cold or something.
Yes.
How can you get chemical reactions ongoing under those environments? I mean,
yeah, I mean, on the surface of the dust grain, then you can have the atoms sitting for 500 or 1,000 or 10,000 years waiting for another atom. So that solves your time problem. And then you get the dust grain heated by the UV radiation, so sometimes the environment is warmer. And that's why you need the dust. You simply need the catalysm of the dust surface to get anything going. And that's why you cannot build dust grains just in space, because you need a three-body reaction. And the temperature is usually too low to have anything happening. So that's why we're absolutely quite certain that anything that happens which is of any molecular interest must happen on dust grains, because we cannot think of any other mechanism where it could happen in space. So, or on planets, of course, but planets are, so to speak, just huge dust balls, right? I mean.
So what about in terms of dark holes? Are the dust inside of those?
Yeah, I mean, they probably contain whatever, stars and dust and things. So the nasty things about black holes from a physics point of view is that you can send things in, but you cannot get anything out. So we don't get any information out, so we don't know what's in there. So you have plenty of room for God and whatever you want to put in there, because we can't measure it. So my guess is, I mean, we have a big black hole in the center of the Milky Way, and we can see stars falling into that, and we can see gas and dust being sucked into that. And if that has happened over the last 10 billion years, then you must have lots of dust and gas and stars lying in there, doing nothing, right? Because then they're sort of out of the whole the whole sort of cosmic recycling. They're like in the waste bin that nobody's going to reuse. They're just sort of gone out of the equation. Time for cocktails, I think. Og? Signe, vil du lukke ballet, eller?
Der er ikke flere spørgsmål, eller hvordan?
Ja. Så vil jeg sige tak for god ro og orden.
Yeah.